Hello everyone, let's do some funky integrals. So we're going to do some more integral calculus using the tabular method in a more advanced way, where typically we want one of our functions in our integrand to be derivable enough times to equal 0, but maybe we'll have a situation where that's not possible, but we can still use the tabular method with some partial integration. For example, let's look at the integral of cosine of x multiplied by etx dx. Now in this case, we have two functions. We can choose our derivable function as cosine, and we can choose our integrable function as etx. And after a few times, we eventually get cosine of x, the first derivative being negative sine of x, and then the second derivative being negative cosine of x. And then each integral of etx is just etx. What we care about is, while we can't derive either of these two functions to the point where we eventually get 0, what we do get is our bottom row, where we have the multiple of e to the cosine of x times etx. We essentially get our integrand again, but just with a different sign. And we can do some pretty nice manipulation with that property. So at this point, typical tabular method, take the diagonals as much as possible. We'll take our first diagonal, cosine of x times etx multiplied by positive 1. Then we'll add to that negative sine of x times etx multiplied by negative 1. And for the bottom row, since we're not multiplying a diagonal but horizontal, we're going to take the integral of that product, the integral of negative cosine of x times etx, and because this is our third term in our tabular method, we'll still alternate the sign by multiplying by positive 1, as if it was another diagonal. So right now we have the integration of cosine of x times etx dx equals cosine times etx plus sine of x times etx plus the integral of negative cosine x times etx times positive 1 dx. Well, nice thing about that is, with that partial integral on the right side, we can pull out the negative 1, so that we're instead subtracting by the integral of cosine x etx dx. That is just the same integrand as what we started with, so let's add that to the other side and combine like terms so that we instead have 2 times the integral of cosine x etx dx equaling cosine of x etx plus sine x etx. Therefore, we can now divide both sides by 2 so that the integral of cosine x etx is just cosine x etx plus sine x etx all over 2. Pulling out some like terms, as is usual, we get our final solution being e to the x over 2 multiplied by the quantity of sine x plus cosine x, and then all of that added to our constancy, integratable constancy. So we're going to do another similar equation or integral, sine of x times e to the x. Just a shout out to a recent channel I got introduced to by one of their comments. There's a channel called Math with Alex, another small channel that's growing. This guy, he does very excellent editing and manipulation with the math that he does, and he's done much more than just integration, but he's already done this integral through the typical integration by parts method, well used in AP Calculus and Calc 2 in college. We're going to solve just a different way, but there will be a link to how he describes how to solve it through another valid method of integration by parts. Now, just using the tabular method though, let's say we take our derivable function as sine of x and our integrable function as etx still. After a few successive derivatives, we get cosine of x and negative sine of x. And then a few integrations, we get e to the x each time. Taking our diagonals, we're going to have our integral equaling sine x multiplied by positive 1 times e to the x. Then we're going to add to that cosine of x times negative 1 times e to the x. And then what we care about is our bottom row, our horizontal. That will be negative sine x times e to the x. And because it is a new term in our right-hand side, we're going to multiply that by positive 1. Because we alternate our terms by multiplying by positive 1 and negative 1, regardless if we're using diagonals or horizontals. Now then, that gives us our temporary solution, which lets us see that we have the integration of sine x e to the x dx on both sides, but one side we're subtracting it, so on the right side, let's add that to the other side. So now that on the left side, we have 2 times the integral of sine x e to the x dx, equaling sine x e to the x minus cosine x e to the x. And then just like before, we can take that and divide by 2, so that the integral of sine x e to the x dx equals sine x e to the x minus cosine x e to the x times 1/2. Pulling out like terms, that's just going to be e to the x over 2 times the quantity of sine x minus cosine x, and then adding in our integration constancy. Math with Alex, he did that through the integration by parts UV method. This is just another method. They're using tabular integration, not necessarily emphasized in AP Calculus AB, perhaps more so AP Calculus BC, as well as usually not so much in Calc 2 in some college courses, but usually by Calculus 3. So a link to Math with Alex, excellent YouTube channel. He's growing, worth a subscribe and a like for that video. And as always, likes and subscribes are not necessary on this channel, but they are fun to see, and perhaps this channel will grow with your help. So let's look at 2 final integrations where we can use the tabular method, but in reality, it would be much quicker if we don't. But let's just take the integration of sine x cosine of x dx. We can take, doesn't necessarily matter, but let's say we derive the function sine of x to get cosine, and we integrate the cosine x function to get sine of x. Well, doing our tabular term method, we get our first and only diagonal being sine of x times positive 1, being sine x squared. And then we can then use our horizontal, our last row, as the integral of cosine of x times negative 1 times sine of x dx. Rearranging a bit just to have it more in line with our first integrand. We can take that term and add it to the other side, take our partial integral and add it to the other side, so that now we have, let's see, 2 times the integral of sine x cosine x dx equaling sine x squared, which, if we just divide by 2, we get the integral of sine x times cosine of x dx equaling sine squared x over 2 plus c. Now, in reality, this is much more appropriate with the typical u-substitution method talked about in AP Calculus AB, and usually in Calc 1 or Calc 2, certainly, where we just use u equaling sine x and du being cosine of x dx, we end up getting, through u-substitution, the integral of u du, which becomes u squared over 2, or sine squared x over 2 plus c. And one more example of where we can use the tabular method, but it's actually much quicker if we don't. But just as a proof of concept, let's say we had the integral of 5 over e all raised to x dx. And just to use the tabular method, let's break up that fraction so that we have 5x times e to the negative x dx. Well, taking our easily derivable function of 5 to the x, and our easily integratable function e to the negative x, what we instead have is 5x deriving to natural log of 5 times 5 to the x. And then our integrated function, we get e to the negative x times e to the negative x integrates to negative e to the negative x. Taking our diagonals and horizontals, each diagonal until we get our last row, which we'll use as a horizontal. The integral of 5x e to the negative x, let's see. All right, there we go. I had to make a little adjustment for the dx term. The integration of 5x times e to the negative x dx, well, we're just going to get our first term being our diagonal, 5x times e times negative e to the negative x multiplied by positive 1, because that'll be the first term on our right side. And then we'll add to that our horizontal, which will be natural log of 5 times 5x multiplied by negative e to the negative x. And because this is our second term on the right side, we'll also multiply it by negative 1. Because we're using a horizontal, we're going to be integrating this and simplifying. Let's see. There we go. Simplifying that partial integral, we have that negative 1 term times the negative sine of e to the negative x. They cancel, and we can pull out that constant natural log of 5 outside our integral. Now what we have is the integral of 5x e to the negative x dx equaling negative 5x e to the negative x plus the natural log of 5 times the integral of 5x e to the x dx. Let's subtract that partial integral on the right side to the other side. We'll have the integral 5x e to the negative x dx as a common term. So we can have our constant being the quantity of 1 minus the natural log of 5 multiplied by 5x e to the negative x dx equaling negative 5x e to the negative x. We can then divide by that constant such that we have the integral of 5x e to the negative x dx as negative 5x e to the negative x all over 1 minus the natural log of 5. Now, just playing around with properties, we can instead rearrange our initial integral as the integral of 5 over e all raised to x dx. That's just equal to negative 5 over e raised to the power of x divided by 1 minus the natural log of 5, which we can simplify that one step further by just taking that negative sign in the numerator to rearrange the signs in the denominator, which just gives us our final integral simplified as much as necessary. The integral of 5 over e all raised to x dx equaling the constant value 1 over the natural log of 5 minus 1 times 5 over e all raised to the x plus our integration constant c. Now, that was just a proof of concept showing that we don't need our partial derivative or our partial integral on the right side to perfectly equal our integrand with a different sign, whether positive or negative. We could have, say, it multiplied by some other integer value. But this is just another example where in reality it's just simple. It's more simpler to not use the tabular method, because 5 over e, that's just a integer, like any integer value raised to x. We can pretend that this is just a raised to x. So the integral of 5 over e to the x dx, it's just going to be 5 over e raised to x times the integral of 1 over the natural log of a, or natural log of 5 over e, which based off of log properties, we can break off that natural log of 5 over e to natural log of 5 minus the natural log of e, which the natural log of e is just 1. So again, we quickly get to our integration of 5 over e all raised to x dx being just 1 minus the natural log of 5 minus 1, or the natural log of 1 over, my apologies. The final solution just becomes 1 over the natural log of 5 minus 1 times all raised to x 5 over e plus our integration constant c. So in some cases, we use our tabular method and we won't have a derivative, we won't have a function that derives eventually to 0. That's okay. We eventually get an partial integral on the right side, which is in essence our original integrand just multiplied by some integer, whether it's by the opposite sign or by some constants. It's possible to still solve our integrals through the tabular method, although, as is usual, there are multiple ways to solve these integrals, and sometimes it's easier to use others as opposed to relying on just one. In any case, always appreciate likes and subscribes. Not necessary, but they do help the channel grow. And please check out the channel Alex Math with Alex. His editing is superb, and he goes into a lot more than just integrals. In any case, just around the 16.5-minute mark. Glad to have you all, and peace.